Let's calculate some more examples of Taylor polynomials using the formula. It's on the board there, it's on the board there. It's 2 times on the board. You can see it here. It's in your notebook. Let's calculate some more examples. So this will be example number 2. Let's do f of x equals e to the x. So first of all, what are its derivatives? So what is e to the x prime? E to the x. What's e to the x prime prime? What's e to the x? K primes. E to the x. So this is e to the x for all k. Do you agree? Right? So what is the kth derivative? Let's call it f, because this is confusing. So what is f, kth derivative, at 0 for all k? It's e to the power 0. So it's 1. Yeah, only natural case. Right? Do you agree? So what are the Taylor polynomials? What is the Taylor polynomial of degree n corresponding to the function e to the x? I just have to plug in 1s for all these derivatives. So I get, okay, f at 0 is 1 plus 1 over 1 factorial times x plus 1 over 2 factorial times x squared plus 1 over 3 factorial times x cubed, and so on. So if I want to stop at n, I stop at x to the n over n factorial. So this is the Taylor polynomial of degree n corresponding to the function e to the x near x equals 0. Good? You could write it using the sigma notation. I don't want to confuse you for now. Let's leave it as this. We will get to the sigma notation, definitely.
Will it be x to the n minus 1?
No, if you want to stop at degree n, you're going to have this, right? 3 over 3 factorial, then n over n factorial. Okay? Let's do one that's slightly more challenging. Let's do, should I erase these beautiful pictures? We don't have a choice, do we?
No. You have them on record. You can write it.
No, but I don't want to erase them. Maybe we'll want to... No. I'll erase this. Here we go. Okay, and erasing this even leaves us the formula down here. So that's even useful twice. Okay, good idea. Okay, so our third example is going to be, let's look at the function f of x equals ln of 1, equals ln of 1 plus x. Okay? So Pn of x equals, the first thing I have to write is the value of the function at 0. What's the value of this function at x equals 0? It's ln of 1, which is 0. So I'm writing nothing, no free coefficient. Did everybody follow? Okay, so no free coefficient, because f at 0 is 0. What's the coefficient of x? It's going to be the derivative of this function evaluated at 0, right? So what's the derivative of ln of 1 plus x? It's 1 over 1 plus x. Do you agree? And evaluated at 0, it's what? 1. So this is this 1, which is the coefficient of x in the polynomial. Clear? Now what is going to be the coefficient of x squared? So I need the second derivative, evaluated at 0, divided by 2 factorial, right? So the second derivative is the derivative of the first derivative. So this is 1 plus x to the power minus 1. So its derivative is 1 plus x to the power negative 1 minus 1 plus x to the power negative 2. So 1 over 1 plus x squared times the inner derivative, but that's just 1. So evaluated at 0, plugging in 0, you get 1, square it, you get 1, 1 over it, you get 1. So all in all, you get minus 1. So we're going to have a minus here, but then you have to divide by 2 factorial. So you get 1 over 2 factorial. 2 factorial is just 2. I'm just writing it. Okay, we can write just 2, right? 2 factorial is just 2. Do you agree? Next. So this was the justification for where this came from. Okay, now we're going to have the next one, which is x cubed. So we're going to need the third derivative. The third derivative is the derivative of the second derivative. So this is 1 plus x to the minus 2. Minus 2 comes down, makes this into a plus 2. So we get 2 over, and then 1 plus x to the minus 3, or 1 plus x to the power 3 in the denominator. Do you agree? Good. When I plug in 0, f prime 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 at 0 equals what? It's just 2. And now, what do I have to write here? Not just this, this, but divided by 3 factorial. So 2 divided by 3 factorial is 6. 2 divided by 6 is 1/3, and now there's a plus sign here. Do you agree? Okay? And you can go on. You can do a few more until you feel that you see the pattern that kind of shows up. And the pattern is that the signs are going to alternate. You're going to have minus, plus, minus, plus. The coefficients are going to be 1/2, 1/3, 1/4, 1/5, and so on. So the general term is going to be plus dot, dot, dot. And the way to write it is plus minus 1 to the power n. So if n is even, you want it negative. So minus 1 to the n plus 1. Now if n is even, you get minus. If n is odd, you get plus. And then you have x to the power n divided by n. Not n factorial, just n. Clear?
We're always going to have to give the general term? We're always going to give the general term?
Depends on what the question is. If the question is find the polynomial of degree n, then yeah, that's what you have to write. If the question is find the polynomial of degree 3, then you stop here. Right?
Is there always a general term?
Is there always a pattern? In most useful examples, yes. Okay? Okay, so
And how do we know that it's like
formally, you recognize the pattern just by observation. If you want to prove it, you need to do some form of either induction or usually, yeah.
You repeat again how you get the last term? The minus
Well, I traced the pattern. I did a few more, and I saw the pattern. The pattern was plus, minus, plus, minus, plus, minus. That is the reason for this negative 1 to the n plus 1. And the coefficients themselves were 1, 1/2, 1/3, 1/4, 1/5, 1/n.
What if we have a tricky one?
Sometimes it's tricky. Then you have to work harder, or maybe you don't see it. Okay, but in this example, it's easy enough to see the pattern. Okay? Okay. Now, before I write the fourth example, I want to very briefly say, let's go back to this board. Let's go back to this board. So everything we did was near x equals 0. All the drawings were near x equals 0. All the tangents and all the lines were all centered at x equals 0. You can run through the entire discussion, including the lemma, including the definition, including these properties, and replace everywhere you see 0 by a general point, call it A. Okay? So then your requirements would be, I'm just replacing all the zeros by A's. Your requirements would be these. I just did something so stupid. Exactly. Instead of erasing all those zeros, I just could have added the tails. Oh, well. Well, I wanted them in blue. So Pn of A equals F at A. Pn prime at A equals F prime at A. Pn prime prime at A equals F prime prime at A. Pn nth derivative at A equals F nth derivative at A. You want all these properties to hold at the point, one second, at the point A. And then you run through the lemma, and the lemma is going to be written slightly differently. Instead of having powers of x, you're going to have powers of x minus a. You're going to have f0. Well, you're going to have, first of all, the coefficients are going to be exactly the same, but evaluated at a. Here, nothing is going to change. But now here, it is going to change. And, well, instead of near x equals 0, it's going to be near x equals a. And here, all these powers are no longer going to be powers. Let me rewrite this, because I need to squeeze it a bit in order to write it. Now it's going to be Pnx equals f at a plus f prime at a divided by 1 factorial, not times x, but times x minus a, plus f prime prime at a divided by 2 factorial times x minus a squared, plus dot, 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 and the general term f nth derivative at a divided by n factorial, I'm just taking these, but multiplying by x minus a to the power n. So this is rephrasing everything around a point A. And we'll do an example in a second. The beautiful thing about rephrasing it around A is that it no longer can be called the Maclaurin polynomial, only the Taylor polynomial. And now I'm safe. I don't have to write it. Good?
Where does the x minus a came from?
So this is a kind of a non-standard way of writing a polynomial, right? Usually we write polynomials as coefficients. All these are numbers. These are the coefficients times powers of x, right? If you write it like this, it's a weird way of writing a polynomial. I mean, if a is 3, for example, then you have x minus 3 squared. X minus 3 squared in itself has x is a polynomial. It has x squares in it, it has x's in it, and it has free coefficients in it, right? So it's a weird way of writing a polynomial, a non-standard, at least as far as stuff you've seen until today. Starting today, this is the standard way of writing a polynomial, at least a Taylor polynomial, around A. Okay? And we'll see an example. That's the next thing I want to do. I want to do an example. Okay? Did everybody have a chance to copy this generalized, well, it's not the generalized, it's just the Taylor polynomial, but not around x equals 0. Okay? Okay, so I'll take the time to erase the board, at least what I don't need. And you finish copying that. I can erase this, and I can erase this. Ah, you're following me. Oh. Okay. Good. So did everybody finish writing this down? No. Now you can say no for 15 minutes and... Did somebody finish writing this down? Yes. Okay, good. Okay, so let's do one more example, not centered around 0. So this was example what? 4. Example 4. Let's take the function to be x cubed minus 4x plus 5. Okay? And I want to find the Taylor polynomial of degree 3. That's what I mean when I write n equals 3. Near the point a equals 2. Okay? So what is P3 of x for this function? Near a equals 2. So what do I need to write? Here I need to write the value of f at the point 2. Right? That's what I need to write here. F at a. So what is the value of f at the point 2? You're too quick for me. So 2 cubed is 8. Minus 4 times 2, that's minus 8. So it's 0 plus 5, so we get 5. Does everybody agree to this? Plus. Now I need to find the derivative of this thing. So f prime of x is what? Is 3x squared minus 4. F prime at 2 equals 2 to the power 2 is 4, times 3 is 12, minus 4 is 8. So I need 8 divided by 1 factorial times x minus 2. Good? Next, plus, now I need to find the second derivative. The second derivative is just 6x. The second derivative evaluated at 2 is 12. So the coefficient here is going to be f second derivative at 2 divided by 2 factorial, 6 times x minus 2 squared. Good? I'm just plugging everything into the formula. Really nothing sophisticated. Everybody following? Okay, plus, and this is the last term. I was only asked for degree 3. So f prime 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 of x is just 6. In particular, f prime 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 at 2 is just 6, divided by 3 factorial, which is 6. So I get 1, and then I get x minus 2 cubed. Questions? Wonderful question. That's what I was going to ask. Why would I want to take a polynomial of degree 3 and approximate it by a polynomial of degree 3? That's a stupid thing to do. Moreover, if there's anything decent in what we're doing, then the best approximation for a polynomial of degree 3 by a polynomial of degree 3 should be itself, for crying out loud. Am I right? Claim it is. This is precisely this. It's just written funny. Okay? It's just written not as powers of x, but rather as powers of x minus 2. If you open this up, and if I didn't do any calculation mistakes, you'd get precisely this. Okay? And approximating a polynomial of degree 3 by a polynomial of degree 3 would really just give back itself. Yes?
That's at any point we choose for a.
At a equals 2, you get it written as powers of x minus 2. If you would do it at a equals 17, you would get it as powers of x minus 17. Okay? So, note, in this case, there is no error. F of x is precisely P3 of x in this case. If you went to higher degrees, the derivative would be 0. You'd get nothing. Okay, so you can't approximate this any better. Okay, you could still approximate it just by the tangent line. You could do that. Okay, that would be an approximation. There would be an error. But you can't do any better than approximating it by P3, because that's it. There's no error any longer anyway. Okay? So the last example I want to give you, example 5, and after that we'll finally write the theorem. So we're going to go back to working around a equals 0, but the function is going to be slightly more interesting. So the function is going to be the following. It's going to be e to the minus 1 over x squared, e to the power minus 1 over x squared, and this is only defined when x is not 0, and when x is 0, I'm just going to define it to be 0. Okay? And how are we doing in terms of time?
Do it with
Oh boy.
degree less, like n is not equal to 3.
More questions about previous examples later. Okay? I want to discuss this now. This function, what we want to do this, we want to find the polynomial around a equals 0 again. Okay? How can you find, what do you need? You need the derivatives at 0, right? The function at 0, the first derivative at 0, the second derivative at 0, and so on. In order to find those derivatives at 0, how do you find the derivative at 0 of this function? Do you just take the derivative of 0?
Limit.
Right. You don't. That would be wrong. You need to take the derivative using the definition of the derivative, which is the limit of f of x minus f of 0 divided by x minus 0. Do you agree? Okay. So f prime at 0 equals the limit x approaches 0, f of x, e to the minus 1 over x squared, minus f at 0, which is 0, divided by x minus 0. Do you agree that this is what you have to do, and this is the limit you have to calculate? Good? And this is very similar to an example that I mentioned last time for L'Hôpital, if I remember correctly mentioning it. But in any case, I'll tell you what's going on here. This is a 0 over 0 situation. You try to do L'Hôpital and it gets you into trouble. You have to rewrite it as the reciprocal, and then it's an infinity over infinity situation, and then L'Hôpital works. I think I mentioned this, but there was actually an x to the power 100 there, or something like that. Remember we mentioned that? Yeah. Okay. So I'm going to put here a dot, dot, dot. There's missing calculations here, which you have to fill in. And after you do those calculations, you get that the limit is 0. So you indeed get that the derivative is 0 at 0 is 0, but not because you just did 0 prime, because of this. And what you get is, therefore, f prime of x in general is 0 when x equals 0. That's because of this calculation. And when x is not 0, you just have to take the derivative of this, right? For any x other than 0. And the derivative of this is what? It's e to the power negative 1 over x squared times the inner derivative, which is 1 over x to the power 3, or 2 over x to the power 3, right? Is there a minus? No, because the minuses cancel. Not 3 to the power 3. No. X to the power 3. Do you agree? So this is f prime. And now you need to find f prime prime. At any point, it's just the derivative of this. At 0, you have to calculate a limit again. The limit of this minus 0 divided by x minus 0. And it's the same argument that repeats itself. And you have to do it again and again and again. Okay? And eventually, there's a big dot, dot, dot here. No, big dot, dot, dot. Because there's a lot of calculations missing. Okay? What you get eventually is the following fact. the nth derivative of this function at 0 is 0 for any n. What does it mean in terms of the Taylor polynomial? Right. The Taylor polynomial, the coefficients are these things, well, divided by n factorial. So if these are all 0, the Taylor polynomial is 0. 0 plus 0x plus 0x squared plus 0x cubed, and so on. Do you agree? So the Taylor polynomial for this function, so Pn of x is just 0. Do you know what one means when I write 1, 2, 3 equal signs? Precisely, everywhere. It's like a stronger equal sign. I've never seen anybody write with 4, but maybe I should introduce that. This is 0 for any n. So by going to higher and higher n's, hoping to do any better, you don't. You're just always stuck with the polynomial being 0. Okay? So the whole theory collapses here. You don't get any approximation. Why? Maybe the function is just 0, but it's not. This is never 0 at any point other than 0. E to the something is never 0. Do you agree? Does everybody see that? So the approximation is always 0. So the error, if I want to write f of x equals Pn of x plus r of x is going to be everything. The error is everything. The approximation is just always 0. Okay? So we're going to see, so what this example demonstrates is the fact that life is not that easy as to be able to say that take a function, well, you need it to be differentiable n times if you want to do this, but if it's differentiable, just take the polynomial, and the higher the n, the better the approximation. Wrong. Okay? There's going to be more work involved after we write the theorem and after we write everything. I just want to add a drawing of this function, what it looks like, because it's kind of mind-boggling. How come that its derivative is always 0? So this function looks like, in fact, it is rather 0-ish near 0. And if you draw it, you'll see that it looks something like this. So near 0, it's in fact very 0-ish, very, very 0-ish. Okay, so this is this function. But it's never 0. Only at x equals 0 itself is it really 0. At all the other points, it's not. Okay? But its Taylor polynomial is just 0. Question?
If we would take the Taylor polynomial at a equals 1.
Different story. Different story. Okay. So let's write the Taylor theorem.
This is the function of e on the power of minus 1 x squared.
Minus 1 divided by x squared.
So it's approximated when it's at 0.
What do you mean it's approximated when it's at 0?
When we're close to 0, the function...
when you're close to 0, at least if you want to approximate it using Taylor polynomials, no matter how far you're willing to go in taking powers, you're not doing any better. The approximation is just 0. Okay? The entire function lives in the remainder, lives in the error. Okay? Let's write, finally, let's write the theorem. It's a very, very good exercise to fill in the dots in that example. Okay? Don't just say, we believe you. Okay? Do it. Well, you need to do it as many times as you need in order to see the pattern and to be able to write the general formula for the nth derivative. Well, proving it would be maybe taking it a step too far, but It would just be some form of induction. So if you want, you can prove it. But at least do the calculations of the limit. Do it 1 or 2 more times. It's good practice. Okay? Okay, theorem. So here comes Taylor's theorem. Let f be n plus 1 times differentiable near x equals a. I'm going to write it right away for the most general case near the point a and not near 0. Let x, let's not write near x equals a, let's just write near a. Let x be any point, a point, in, okay, I'm going to fix it again, sorry. Instead of near a, I'm going to write in a neighborhood of a. And let x be a point in that neighborhood. Sorry, I apologize for the mess in your notebooks. Okay. Then there exists a point C. So we have A, we have X, we have C. I told you it's a mouthful, but we're going to decipher it carefully after we write it. There exists a point C between A and X such that f of x equals Pn of x plus Rn of x I want to pause here a second. That there's going to be another line, but I want to pause here a second. Pn of x is the Taylor polynomial, which I don't want to write its formula again because we wrote it several times. Okay, it's still on the board. So that's Pn of x. Just saying that f of x equals Pn of x plus Rn of x is saying nothing at all. Okay, why? Because if you give me any function, give me a function, make it nasty.
X squared by 4x.
Directly, good. That's nasty. Do you agree? Directly. I can write directly as a Taylor polynomial or as any polynomial you want plus a remainder. Ready? Ready? So don't write this. Don't write this. Don't write this. Directly, let's call it d of x for now. Remember directly? 1 on the rationals, 0 on the irrationals. Nasty. Right? Not continuous anywhere, not differentiable anywhere. Nasty. Directly equals, give me your favorite polynomial.
X squared.
X squared. X squared plus minus x squared plus directly. Do you agree? I just wrote directly as a polynomial plus something. Duh. You can always do this, but it doesn't say anything. It's meaningless. Do you agree? So the only way that a theorem like this is going to be meaningful in any sense is if by some way you can control the remainder. If you have a statement that in some sense says what we said imprecisely in the previous hour, that somehow this is less than epsilon, somehow this is small. Okay? And the way to say it, okay, is the following. The way to say it is the following. And there are several ways of stating this theorem, by the way. I chose one of them. Rnx is not anything. It can be described very precisely. It's the n plus 1th derivative of the function, n plus 1th, or n plus 1st, I don't know how to say it, at the point C, at this intermediate point, which we don't know what it is, divided by n plus 1 factorial times x minus a to the n plus 1. Because that's Rnx. Okay, C only shows up here. So the entire polynomial was made up of terms exactly like this, with smaller and smaller n's, but where this was a. Now the statement is that the remainder has this precise formula. Okay, this is called, so maybe let's write some remarks. Yeah, I'm going to have to erase these pictures. Damn. Okay. But they were beautiful. That's true. They're recorded. They have eternal life. We don't. Well, anyway, remarks. So that's Taylor's theorem. Remarks. So, remark number 1, f of x equals pnx plus rnx. This is the Taylor polynomial, which we wrote previously. And this is called the remainder. That's what it's called. And the whole idea, which we're going to explore, we're not done, we're going to explore this, it's going to take us another hour, is that using that formula, and there are other forms of formulas for the remainder, we can show that it's small in some senses. Okay? So the formula that I wrote is called the remainder in Lagrange. Remember him? Lagrange form. There are other forms for the remainder. I'm only going to mention this one. Okay? Remainder in Lagrange form. Rnx satisfies No, this is still part of the remark. Rnx satisfies that as x approaches a, Rnx approaches 0. But moreover, even if you divide by x to the n, or in general by x minus a to the n, it still approaches 0 as x approaches a. When we started by working with the tangent line, we said this for n equals 1. We said that the remainder, okay, so we said that the remainder, which was f of x minus p of x, right? R of x is just f of x minus p of x. Remember we did that? F of x minus p of x approaches 0. And then we said even if we divide by x, f of x minus p of x approaches 0. And this is the general fact. Okay? It approaches 0 as you approach the point, even when you divide by powers of x minus a up to the nth power. Okay? That's saying the power of the approximation. And one more remark. And we're going to stop after this remark because we're out of time, but we are going to devote another hour to this. For example, to see how we actually work with Taylor polynomials. What are they useful for? That we'll do next time. So the second remark is, let's look at the theorem again. I know, this really is a mouthful. This really takes time to absorb and to get used to, and we'll continue next time. But usually when you want to understand something general, look here a second. Usually when you want to understand something general, it's a good idea to start for small n's, not with the general n. Okay? So what would be a small n that you would recommend to start with in order to decipher it? 3, 2, 1, 0. Let's start with n equals 0. That should be something very, very trivial, right? If n equals 0, what's p0 of x? F of 0. Do you agree? P0 is just the value of the function. Well, not f of 0, f of a. F of a. So f of x equals f of a plus, when I plug in 0, what do I get? I get f 0 plus 1, first derivative, at c, divided by 0 plus 1, 1, factorial, that's like doing nothing, times x minus a. Let's write that. For n equals 0, the most trivial case, we get f of x equals f of a plus the remainder, which is f prime at some point c divided by 1 times x minus a. Do you agree? And this, if you subtract f of a, divide by x minus a, you get f of x minus f of a divided by x minus a equals f prime at c. What did we just get? Lagrange's theorem. Lagrange's theorem. Lagrange's theorem factorial. Right? So for n equals 0, that Taylor's theorem collapses to just being Lagrange's theorem. There exists a point between x and a such that the derivative at that point equals precisely this. Do you see that? So Taylor's theorem, in this sense, is a big generalization of just Lagrange's theorem. Okay? So next time, we're going to do an example of how we use Taylor's theorem to do calculations, and how we control the remainder, and how we can use that in order to draw conclusions. And we're going to discuss the one issue that is still unclear. How does making n bigger and bigger help us in getting better and better approximations? We know by the last example that we had that that's not always going to be the case. There are going to be conditions that guarantee it. Okay? So, see you next time.